Hi everyone, welcome back. Today onwards we are going to start a new course on Kaggle, that is computer vision. We have 6 lessons to complete. First we will do the tutorial, then we are going to do the exercise. Okay. Now before that let me give you a small recap. If you have idea about deep learning, then you know that deep learning starts with ANN, that is artificial neural network. It is simple neural network used for different kinds of predictions. Okay. Next, CNN, which is known as convolutional neural network. This is mainly used for image classification, video processing, all these things. And next is RNN, recurrent neural network. This is mainly used for NLP purpose, speech recognition, all these things. We are going to complete this course. Okay, now let's start. The convolutional classifier. Create your first computer vision model with Keras. Keras is a deep learning library. So using that library, we are going to create our first computer vision model. Okay, let's start. Welcome. Have you ever wanted to teach a computer to see? In this course, that's exactly what you are going to do. You are going to teach your computer how to see. Okay. So these things you are going to learn, and if you have taken the introduction to deep learning course, then you know everything you will need to be successful. I hope you have done this. I also explained this course. Okay. Otherwise it will be difficult for you to understand. Basic deep learning concept is required. Okay. Introduction. This course will introduce you to the fundamental ideas of computer vision. Our goal is to learn how a neural network can understand a natural image well enough to solve the same kinds of problems the human visual system can solve. Simply, if I look at any flower, I can tell which flower is this. I want my computer to understand the same way. It will see the flower and it will tell me which flower is this. That is computer vision. Now the neural network that are based at this task are called convolutional neural network, or we can say ConvNet, or we say CNN. Okay. Convolution is the mathematical operation that gives the layers of a ConvNet their unique structure. In future lessons, you will learn why this structure is so effective. But before that, you have to learn how to build that structure. Now, we are going to apply these ideas to the problem of image classification. Given a picture, can we train a computer to tell us what it's a picture of? You have seen many apps like Google Lens. You have seen that if you scan any image, it will tell you which types of picture is this. What kind of picture is this, right? That is an image classifier. So in this course, you are going to learn how to build an image classifier just as powerful as those used in professional applications. Now, while our focus will be on image classification, but this is very relevant to every kind of computer vision problem. Fine. Now the convolution classifier. A ConvNet, and at the end you will be ready to move on to more advanced applications like generative adversarial network or image segmentation. Fine. Okay. The convolutional classifier, how it looks like. See, it has two parts. One is base and another is head. This is convolutional base. This is dense head. What base part does and what head part does. Now the base is used to extract the features from an image. And any image, let's say this is the car. What are the features of this car? The headlights, the steering, the gear, wheels, the color, any kind of line. These are the features of a car, right? So every image has some features. So base part extracts those features. And what head does? Head classifies them. Okay. So the base is used to extract the features from an image. It is formed primarily of layers performing the convolution operation, but often includes other kinds of layers also that we are going to learn later. And head is used to determine the class of the image. Clear? So base extract the features, head tells us which kind of image is this. Okay. Now what is visual feature? That is what I have already told you. Line, texture, shape, pattern, or some complicated combination. And after you have extracted the features by your base, now your head is ready to tell you which types of image is this. Okay. Now, how to train the classifier? You have to train the classifier. So, you have to train two things. One is which features to extract from an image, that is done by base. which class goes with that features, that is head. Now these days coordinates are rarely trained from scratch, because to start anything from scratch you need a huge amount of data that you don't have simply. So what you do, you take the pre-trained base model and you add some of your own so that you can just manipulate it to classify your own image. Clear? So what we do, we reuse the base of a pre-trained model. To the pre-trained base, then we attach the untrained head. So clear? I just want to say that it has base, it has head. This is base, head. Now this base is already old. It has been trained on many images. So what do? We just simply import this. And with this is the untrained part that we are going to create. If we want, we can give 3 layers, 4 layers, 5 nodes, whatever your wish is, you can create your own head. So this part is in your hand, right? This is untrained, but base part is already trained. So we are going to import this, we are going to define this, then our classifier will be ready. Clear? Simple concept. Now, to the pre-trained base, then we attach the untrained head. In other words, we reuse the part of a network that has already learned to do. Extract features. Extract features, it has been already learned, because this part is extracting the features. So, I am not telling my model how to extract features. This one is already trained on many networks and it knows very well how to extract features. I am just telling to classify. Once it has extracted the features, like what is the line, what is the color, what is the texture, then my neural network will tell to classify the image, whether it is a car, whether it is a bus, whether it is a truck. Clear? Now, because the head usually consists of only few dense layers, very accurate classifiers can be made from relatively little data. Because this is already trained and very good. So here we have some thousands of data only, very little data, but our head can easily classify. Okay. Now, so reusing a pre-trained model, this is already trained and we are reusing this. This technique is called transfer learning. In deep learning, you have to learn about this concept because you are going to use pre-trained model many times. So you have to know about transfer learning. Okay. Now example, train a coordinate classifier. So now our main job starts. So what we have to do, let's say we want to know whether any image is of a truck or of a car. So we have to create a model that will take the image and will classify you whether it is a car or truck. That is your job. Okay. Now what you have to do? You have to provide so many images, whatever you can, let's say 10,000 images, right? So first you have to give 10,000 images. In the model, you have base, you have head. This is the base part, this is the head part. Base part, you have to just load, which is already pre-trained. You don't have to do anything else. But in head part, you have to create your model. You have to create your network, neural network, and then you will classify whether it is a car or a truck. Fine. Now, as this is already trained on a huge amount of data set, huge amount of data set, that is why even with a small numbers, you are performing well. Clear? This is the whole thing. I have just connected the dots. Okay. Throughout this course, we are going to learn the creating classifiers that attempt to solve the following problem. Is this a picture of a car or a truck? Our dataset is about 10,000 pictures of various automobiles. Fine. Load data. This is the code. This is just for loading the data, some library, setuping data pipeline. This is the training dataset. This is the validation dataset. Okay. I hope you know what is training dataset, what is validation dataset. Now define pre-trained base. Base, pre-trained. So most commonly used dataset, you know, ImageNet. On ImageNet, many models are trained in Keras. One of them is VGG16, so we are just going to import VGG16. Simple, just importing a already trained model. We are not doing anything here. Here is the part where we can do something, that is attaching head. We attach the classifier head. So we will use a layer of hidden units, first dense layer followed by a layer to transform the outputs to a probability score for class 1. See, this is the pre-trained base we have imported, nothing to do here. From here we are starting the head part. So we are using flatten layer. Flatten layer just helps you if the pre-trained base output looks like this in two-dimensional form, then flatten layer will make it one-dimensional. Then only you can pass it through different neural networks. Okay, now this one you will create. So here it has created layers.dense 6. That means there it will be 6. 1, 2, 3, 4, 5, 6. Okay. And what is the activation function? Activation function, you know, for first one they have used ReLU. For second layer, they have used sigmoid. ReLU, what is the function of ReLU? Max of 0, x. That means it will not pass anything negative. Either it will be 0 or it will be positive. If it is positive, it will remain as positive. If it is negative, then it will become 0. That's what ReLU activation does. And sigmoid squashes the value between 1 and 0. Okay. What is the function? 1 by 1 plus e to the power minus x. These are the activation functions. I hope you have idea about these things. These activation functions actually helps to introduce non-linearity. This is a basic concept. Anyway, let's come back to our point. So this is how we have created head. Now we have to train the model. Now the main step, that is training the model. So finally let's train the model. Since this is a two-class problem, we will use the binary versions of cross entropy and accuracy. Two-class problem means they just want to check whether it is a bus or a track. That is why they are using binary cross entropy. Okay. And matrix is accuracy. Here you can use many other things also. And optimizer, they are providing Adam. Okay. Why optimizer is used? Optimizer is used to adjust the weights during the training. And loss will calculate the loss. What is the difference between the predicted value and the actual value? Okay. And matrix helps you to understand how your model is performing. Okay. Now once it is done, now you are creating a history. So you are training the model and you are keeping it in the history so that you can later see how your model is performing during the training. Okay. While training a network, it is always a good idea to examine the loss and metric plots, and that is done by history. So history object contains the information in dictionary history.history. We can use the pandas to convert the dictionary to a data frame and plot this in built-in method. See, we are plotting how it is performing during training. See, this is loss, this is validation loss. So your training data is performing this way, your validation is performing this way. So this is, you can, if you know, you can see this is overfitting and this is the accuracy. See, this is the normal accuracy, this is validation binary accuracy. Okay. We will learn how to solve later. Now conclusion. In this lesson we learned about the structure of a component classifier, a head, a base. A base performs the extraction, head classifies. The head essentially is an ordinary classifier like you learned in the introductory course. Exactly. For features, it uses those features extracted by the base. Base has extracted the features that is used by the head. Head is just a classifier. This is basic idea about convolutional classifier. Okay. So this is one of the big advantages deep neural network have over traditional machine learning, that given the right structure, the neural network can learn how to engineer the features it needs to solve the problems. Okay. Now your turn is to build your own image classifier. That is interesting. Okay, so let's start the exercise. So in this tutorial, we saw how to build a classifier by attaching a head to dense layer to a pre-trained base. Okay, now the base we used from a model called VGG16, and we saw that VGG16 architecture was prone to overfitting. Exactly, we saw that. See here, you can see that validation loss after a certain time is again getting increased. So simply this is overfitting. Anyway, so in this course we are going to learn a number of ways to improve the initial attempt. Okay. So first you will see how to use the base more appropriate to the dataset, and the base of this model is called Inception V1 or GoogleNet. Inception V1 was one of the early winners of ImageNet competition. ImageNet, I told you, that's a database of many natural images, and one of its successor, Inception V4, is among one of the state of art today. Okay, no problem. To get started, you have to run this cell to set up everything, and once it is done, the Inception V1 model pre-trained on ImageNet is available in the TensorFlow Hub repository, but we will load it from a local copy. Okay, so it's done. And now define pre-trained base. Now that you have a pre-trained base, to do our feature extraction, decide whether this base should be trainable or not. You just have to check that this is already pre-trained, but can I retrain it or not? So if I give, let's say I give true, that means I want to retrain it. Now see what is the output. What happened? See, incorrect. The base should not be trainable. Since it's already been pre-trained on a large data set, you can expect that it will be hard to improve. Exactly. So that means I cannot train it because it is already trained in large data set. See, when doing transfer learning, it is generally not a good idea to train the entire web database. Okay, the reason is that random words will create large gradients that will destroy much of the pre-training. Fine tuning, if you have idea, then you can do this, but generally it's not a good idea. Okay, so we are not going to train the base. So we are going to do the head only. Okay, now see, this is what the head structure will reflect. Now that the base is defined to do the feature extraction, so you have to create the head so that it can classify, right? Now see, you have to write your code here. First you have to do flatten, that is already they have done. Now you have to do dense layer, unit 6 activation ReLU. Simply you have to just write layers dot dense. Here can I copy? No, this is an image, so I just have to write units equal to 6, activation equal to ReLU. The same thing. Okay, second one, let me copy this, paste. Here units is 1, activation is sigmoid. Okay, now let's check it. Sorry. Okay, now next, train. Now you have to train the model. So your base is loaded, your head is created. Now you have to train the model. See, before training the model in Keras, you need to specify an optimizer to perform gradient descent. Optimizer is required to adjust the weights. A loss function that will calculate what is your loss and any performance metrics. Okay, so the optimization algorithm is used Adam. They have already said Adam. Okay, they have provided here, who generally performs so well. Okay, the loss and the metrics you have to provide. So the loss is, let's give, our problem is binary classification problem. So the car coded as 0 and the truck coded as 1. So choose an appropriate loss and appropriate accuracy matrix. So binary classification means they just want to give binary cross entropy. Binary cross entropy is a way of calculating loss. Here our problem is binary classification, either 0 or 1. So just go for binary cross entropy. You can give any loss function, but here it is best. Okay. And what is the matrix? Let's give binary accuracy. So can write binary underscore accuracy. Okay. Now let's run it. Sorry, binary cross entropy. Fine. Now, history, it will save how the model is performing. So let me run it. Okay, now this is done. Here I have changed the epochs to 5 from 30 because it was taking time. And in every epoch you can see what is the loss, what is the binary accuracy, what is the validation loss, and what is the validation binary accuracy. Okay, now this is plotted. Here you can see the loss, validation loss. See, this one is loss for training data and this one is loss for validation data. Okay, this one is loss for binary accuracy for training data and this is binary accuracy for validation data. So you can plot whatever you have got from the history. Okay, now do you notice a difference between these learning curves and the curves for VGG16 from the tutorial? Yes. What does this difference tell you about what this model and learned compared to VGG16? Are there ways in which one is better than the other? See, you have to check this one. Here you can see this was our loss, validation loss, this was our binary accuracy, validation binary accuracy. But here the loss curve and this curve is different. So this was used VGG16 model and this one is Inception V1 model. Now they want to know which one is better, which one is yours. Okay, you can try to tell. See, the training loss and validation loss stay fairly close in evidence that the model is not just memorizing the data but rather learning. That means you are reducing the overfitting. Okay, now but because the model converges at a loss greater than the VG16 model, it is likely that it is underfitting. So you have to balance the both. You have to stop overfitting, you have to not stop, but you have to reduce overfitting and also reduce underfitting. Okay, so you have to understand which one is giving you the maximum benefits. Okay, so in the first lesson you learned the basics. You have consist of a base which extract features, head which decided the images class, and you also understood how to build a classifier with transfer learning on pre-trained base. Okay, so in our next class we are going to learn about lesson 2. Till then, bye, happy learning. Hi everyone, welcome back. In our last class we started computer vision and we have completed our first chapter, that is the convolutional classifier. And today we are going to study about convolution and ReLU. Okay, so let me first read it, then we will do the exercise. So in the last lesson we saw that convolutional classifier has two parts. If you remember, it has two parts. One is base, another one is head. Why convolutional layer is used? To identify an image. You will be given an image and you have to tell what is the type of the image. Is it a car? Is it a bus? Is it a truck? Is it a boy? Okay. So for that you need convolutional layer, CNN. This is the convolutional layer and it has two parts. One is base part, another one is head part. Base part is used to extract the important features from the image. And head part will classify the image. That means it will tell you what is the type of the image. Okay, now in today's class we are going to understand what is there inside the base class. Okay, so this is our main job today. Now see, in next few lessons we are going to understand about two most important types of layers: convolutional layer with ReLU activation and maximum pooling layer. In lesson 5 you can create your own coordinate. Okay, so first is feature extraction. This is the best part to extract the features. So you have to learn how to extract the features. This is the input image. Okay, so first we will understand what is the purpose of these layers. We are going to see how these layer operations are used to implement feature extraction process. So feature extraction is performed by three basic operations. One is filtering the image, detecting, and then condense. See, first you are doing the filter. So you can see that you can understand what are the edges. See, these are the edges, right? These are the edges. Then you detect. Okay, and after that you do the condense. See, filter is done by convolution. Okay, so you are filtering the image. Second, you are detecting the feature within the filtered image. That is done using ReLU. This is the ReLU part. Next, you are condensing the image to enhance the features. You can see this image and this image. Here, the things are more enhanced. This part is done by maximum pooling. Okay. So, 3 steps. One is filter, detect, condense. Filter is done by convolution. Detect is done by ReLU. Condense is done by maximum pooling. Okay. Things will be more clear. No worries. The next figure you can see, this is the figure we have seen already. Now that network will perform several extractions. It's not that it will do only one job, but it will perform several extractions from the single image. So it's not uncommon for the final layer to produce 1000 unique visual features. Okay. Now the first one is filter with convolution. A convolutional layer carries out the filtering step. You might define a convolutional layer in Keras model something like this. See this one. From TensorFlow import Keras. From TensorFlow.keras import layers. Okay, these are the things you are importing. Here your convolutional layer is defined. So next is you are creating the model. So layers.conv2d filter equal to 64, kernel size equals to 3. Now let's understand this part. See, first you are given the image. Image means this is collection of pixels. That is values. So I can write, let's say 1 2 3 2 1 0 1 2 1 0 3 2 1 2 3 1 0 1 0 1 2 1 2 1 2. Whatever value if you want to take, you can just take. Okay, this is your image, or I can say input. Fine. Next you take filter, or we can say kernel. See, we have said. So you are taking 64 filters. And what is the kernel size? 3. So I have taken 3 by 3. 1 2 3 1 2 3. 3 into 3. Right? Now what will you do? Now you have to impose this complete part on this part. And there will be a matrix multiplication. So let me show you one. So first part will be 1 2 3 0 1 2 3 2 1. This portion into 0 1 0 1 minus 4 1 0 1 0, this part. Okay. Now what you have to do? You have to do the multiplication. You know how to do matrix multiplication? This way, this way. Then you will never get confused. Right? So I am taking 1 into 0. So 1 into 0 plus. I said this way. So you have to take this one, 2. But here I have said in this way. So you have to take this one into 1. Now 3 into 0 plus this way, second column this way. So first is 0 with 1. 0 into 1. Next is 1 with minus 4. So 1 into minus 4. Next one is 2 into 1. So 2 into 1. Okay. Plus this row, last column. So 3 into 0. 3 into 0 plus 2 into 1. 2 into 1 plus 1 into 0. 1 into 0. So if you add them, let's say you get x. You get my point? This is how this is done. Why, that you will understand later. Let me first explain how. So your output will be, let's say, x. Okay. Now what you have to do? Now you have to take these 3 values with this image, with this filter. Okay. So next time it will be, show you one more, 2 3 2 1 2 1, this portion, the blue one. Okay, 2 1 2 with the filter 0 1 0 1 minus 4 1 0 1 0. Same way multiplication will be done. Let's say the value will be y. Clear? Now you have to move by one row. So this 3. It will be multiplied with this one. Let's say you get z. Clear? Next, you have to come here and you have to take 3 by 3. This part. So let's say A. Again, you are moving by 1. So this portion. So it will be B. Second, next, it will be this one. Let's say C. Done. Now, again, you have to take these 3. So it is D. Now you have to take this much E. And now you have to take this portion. Let's say F. Okay. So see, this was the image input. This is the output. Clear? This is how the operation is performed. Now let's read more. Things will be more clear. Okay. So kernel size equals to 3 means you are taking 3 into 3 size. Okay. And filter 64 means you are taking 64 filters. 64 filters. Fine. Now we can understand these parameters by looking at the relationship to the weights and activations. Weights. The weights of a coordinate layer during training are primarily contained in the convolutional layers. See this one. This one. Convolutional 2D. Here the weight is contained. These weights we call kernels. Okay. And it looks like this. Fine. Now see, kernel operates by scanning over an image and producing a weighted sum of pixel values. See, that's what I have told you. You are just taking this one and you are scanning over the image slowly and you are producing this output. A kernels define how a convolution layer is connected to the layer that follows, and it can be of any size. Especially odd number dimension is better, but that's not a requirement. Like we have taken 3 by 3, same you can take 5 by 5. Odd one is better so that one pixel sits at the center. Okay. Now next one. The kernels in convolution layer determines what kinds of feature it creates. During training, a coordinate tries to learn what feature it needs to solve the classification problem. This means finding the best value for its kernels. Okay. So while training, it tries to learn that which one is giving you a better solution. Okay. So it is actually finding the best values for the kernels. Activations. Activation means the activation in the network we call feature maps. These are feature maps. Okay. These are the result when we apply a filter to an image. You have applied different kinds of filter. So this is one feature map. This is another feature map. This is another feature map. These are the pixel values and these are the pictures. Okay. So here are few kernel pictures with feature maps. Okay. Now from the pattern of numbers in the kernel, you can tell the kinds of feature maps it creates. Generally, what a convolution accentuates in its input will match the shape of the positive numbers in the kernel. The left and middle kernels above will both filter for horizontal shapes. With the filters parameter, you tell the convolutional layer how many feature maps you want it to create as output. I told you that we have given filters equal to 64. That means you are getting 64 feature maps. Clear? So you are doing filtering using 64 filters and you are getting 64 pixel values with 64 feature maps. Clear? With the filter parameters you can tell. Now detect with ReLU. So as of now we have completed this part. Filter an image for a particular feature. Clear? Now let's move to the detect part. That is done using ReLU activation function. See, after filtering, these feature maps pass through activation function. The rectifier function has a graph like this one. This one is the ReLU function graph. A neuron with a rectifier attached is called a rectifier linear unit. This is the full form of ReLU. Okay, there is a rectifier. For that reason, we might also call the rectifier as ReLU function. The ReLU activation function can be defined in its own activation layer. See, this one is here. You have given activation is none. There is no activation. But the same thing, you have just changed the activation equal to ReLU. Okay. The same code you can see. keras.sequential convolutional layer giving 64 filters, kernel size is 3. You are just adding activation equal to ReLU. Fine. Now you could think about activation function as scoring pixel values according to some measures of importance. Now the ReLU activation says the negative values are not so important, so sets them 0. See, these are the feature maps. You have got it from convolution, and these are the pixel values, and these are the feature maps, right? See, this one, these three, you have used 3 filters. Fine. Now ReLU says that you have got some negative values, see, -2, -1, -1, -1. So ReLU says that these are not important. You don't need any negative values, but replace them with 0. So like other activation functions, ReLU function is a non-linear function. This is there are many other activation functions. Here we are talking about ReLU function, and the job of ReLU is to make the negatives as 0. So that's why the graph is like that. There is no negative value, you can see. If anything is negative, it will be 0. Okay, only positive values will be remained and negative values will become 0. That's why the graph is like this only. Okay, now let's do an example. Let's apply convolution and ReLU. So we will do the extraction ourselves in this example to better understand what convolution and networks are doing behind the scenes. This is the image. Okay, now see. For filtering step, we will define a kernel, then we will apply it to the convolution, right? The kernel is in case the edge detection kernel. Kernel helps us to detect the edges. You can define it with tf.constant, just like you would define an array using np.array. See, import TensorFlow kernel equal to tf.constant, and you are defining your own kernel. Okay, this is the figure size is 3,3 and show kernel. See, this is the kernel. Okay, now TensorFlow includes many common operations performed by tf.nn module. These two we will use conv2d and ReLU. Okay, so next, hidden cells does some reformatting to make things compatible with TensorFlow. If you want, you can just go through this. This is your image and kernel. Now let's apply the kernel. See, tf.nn.conv2d. These are the function. This will help to apply the kernel. Input is the image. This one is our input. Filters equal to kernel. This is our filters. Strides equal to 1, padding equal to same. These things I will tell you later. And now you are taking the figure and you are getting this output. This is your filtered image. Okay, so here you can see you have applied convolutional 2D. Next step, adding the ReLU function. This function is much simpler than convolution as it doesn't have any parameters to set. So here you just have to write tf.nn. tf.nn, as they have told you, that some operations performed by tf.nn module, right? Again, you are using ReLU. So plot figure, the same figure, show the image, and now after activating ReLU. This was before ReLU, this is after activating ReLU. So what it has done, from these feature maps, the pixel values, negative pixel values are transformed to 0. Okay, only the positives have given the priority because ReLU thinks negatives are not required. Now we have created a feature map. Images like this are what the head uses to solve the classification problem. We can imagine that certain features might be more characteristics of cars and others are in trucks. So the task of a coordinate is to create kernels that can find those features. Okay, so we saw in this lesson the first two steps: a coordinate, filter with conv2d layers, and detect with ReLU. So we have completed these two parts. One is filtering, another one is detecting. Okay, so filter will give you some feature maps and ReLU will remove the negatives, make them 0 and keep the positives. And in our next class we are going to understand the third part. Once you understand all of them, then you complete this particular base part. Okay, now let's do the exercise. In this exercise, you will work on building some intuition around feature extraction. First we will walk through the example we did in the tutorial, but this time with a kernel you choose yourself. We have mostly been working with images, but what's behind all of the operations we are learning about is mathematics. See, first let me run this to get started. Then you have to apply transformation. The next few exercises walk through feature extraction just like the example in the tutorial. So let's run this. Now import, you can run this cell to see some standard kernels used in image processing. See, kernel, edge, serpent, these are the different kinds of kernels. So see, this is the gray image and these are the different types of kernels. Okay. Now use the next code cell to define a kernel. Now this is your job. You have your choice of what kind of kernel to apply. One thing to keep in mind is that sum of the numbers in the kernel determines how bright the final image is. So generally you should try to keep the sum of numbers between 0 and 1. Though that's not required. In general, a kernel have any number of rows and columns. For this exercise, let's use a 3 into 3 kernel which often gives the best results. Define with df.constant. So see, it is better that you keep the sum of the numbers between 0 and 1. Okay, so let's take the kernel from here. This is how you have to define the kernel. So let me just paste it here and we can change the numbers. Let me give -2. So -2, -3, -5, -6. So let's give 1, 0, 2, 1, 2, 3, 4, 6, 1, 7. So -6 plus 7, it will be +1. Let me run this. See, correct. So you just try to keep the numbers between 0 and 1, though that's not mandatory. Okay. This is how you can define your own kernel. You have to just give 3 rows, 3 columns. Now let's uncomment to view the kernel. You just have to uncomment this one. See, now it is fine. Okay, this is the kernel you have given. Okay, now we will do the first step of feature extraction. First run this cell to do some reformatting for TensorFlow. Fine. Now we will apply the kernel to the image by a convolution. The layer in the keras that does this is layers.conv. You do know that what is the backend function in the TensorFlow that performs the same. We have already read tf.nn. So the backend function is tf.nn.conv2d. Okay, but you don't need to write this because Keras is already doing. You can just use layers.conv2d. Okay, but this is the backend function. Fine. Let me run this. Fine. Now, once you have got the correct answer, run this next code cell to execute the convolution and see the result. See, this is the image filter. You can see input is image, filters equal to kernel, strides 1, padding same. This is the image show. But there is a problem. Why? Okay, now apply ReLU. Now detect the feature with ReLU function. In Keras, you can do it conv2d. There you can write activation equal to ReLU, but what is the backend function is same. For both case, it is tf.nn.module, that is ReLU. Okay, now let me run this. Okay, now once you have got the solution, run the next code cell to see the image. This is the image after activating ReLU. Before, after. Okay. In this tutorial, our discussions of kernels and feature maps was mainly visual. We saw the effect of conv2d, convolutional layer, with ReLU activation function by some images. But the operations in a convolutional network, like all neural networks, are usually defined through mathematical functions, through a computation of numbers. In the next exercise, we will take a moment to explore this point of view. Let's start by defining a simple array to act as an image. See, this is a simple array, but no image is showing. Observe convolutional on a numeric. What do you see? The image is simply a long vertical line. I can't see any image. Is there any image? But where is the image? A long vertical line will be the image on the left and a short horizontal line on the lower right. What about the kernel? What effect do you think it will have on this image? You can think that how the pattern of positive numbers will tell you what kind of features the kernel will extract. The kernel has a vertical column of ones, so we could expect it to return features of vertical lines. Now let's try it out. Run the next code cell to apply convolution and ReLU to the image and display the result. Here the image is not showing, I don't know why. In this lesson you learned about two operations. Okay, we have got the main point, that is filtering an image with a convolution and detecting the features with ReLU, rectifier linear unit. And in the next one we are going to read about condensing for using maximum pooling. Then our best part will be completed. Okay, so meet in our next class. Till then, bye. Happy learning. Hi everyone, welcome back. So let's continue computer vision course. And as of now, we have completed convolutional classifier, convolution and ReLU. And today we are going to study the third lesson, that is maximum pooling. Okay, first we will read the tutorial, then we will do the exercise. But before that, let me give you a small recap. We know that a convolutional classifier contains two parts. One is base part, another one is head part. What is the job of the base part? To extract the features. To extract the features from an image. And what is the job of the head part? To classify the image. Right? Now in base part, you have three jobs. One is filter. Filter is done by convolution, that we have already understood. The second part is detect, which is done using ReLU activation layer, and the next one is condense, which is done by max pooling. Okay, we have already completed these two parts and today we are going to do this one. Okay, so let's start. In lesson 2, we began our discussion of how the base performs feature extraction. We learned about how the first two operations occur in convolutional 2D layer with ReLU activation, and in this lesson we are going to study condense with maximum pooling. It is done by maximum pool 2D layer, okay, which is already in Keras. Okay, now condense with maximum pooling. See, Keras imported, layers imported, same Keras.sequential, and this one we have already understood that it is a convolutional layer. Filter, you are using 64 filters and kernel size equal to 3. If you remember, let me show you. This was the kernel size, 3 by 3, 3 rows, 3 columns, and you are taking 64 kernels or 64 filters, and what you are doing, you are imposing this on the image and you are trying to get the features, right? This is done by convolutional layer, this one. Now, once you have done this, you apply activation, but here they have not given any activation layer, but we applied ReLU. If you remember what ReLU does, ReLU makes the negatives to 0, right? Now next one is, once ReLU has performed its work, now what you do, you enhance the features. You see here, first step is filter, that is done. Second step is detect, that is done by ReLU. Now this one is enhancing the features. You can see the difference one. Okay. Now see, a max pool 2D layer is much like a conv 2D layer, except that it uses a simple maximum function instead of a kernel. In conv 2D layer you are using a kernel, right? But in max pool 2D layer it is a simple maximum function. We will understand. Okay. And with the pool size parameter analogous to kernel size. And a max pool 2D layer doesn't have any trainable weights. Nothing like that. You will understand that. Like a convolutional layer does in its kernel. Here we are training, we are trying to find which one is the best. But in case of maximum pool layer, no trainable weight is there. There is a simple logic, you have to find which one is the maximum. Okay. So let's take another look at the figure. Fine. Notice that after applying the ReLU function, the feature map ends with a lot of dead space. Why? Because you have seen that when you apply ReLU, if there is any negative pixel, what does ReLU do? ReLU makes it 0. So what it becomes? It becomes actually a dead space. It has a position, but it doesn't have any value. So large areas containing only zeros, the black areas in the image, and carrying these zero activations through the entire network would increase the size of the model without adding much useful information. So you understand the problem? The problem is that you have made the negative 0. Now the 0 are taking space and they are of no use, no information. Those are only black space. So what you are doing, you are increasing the size of the model, but you are actually not getting any information. That's why we do the condense. So you understand why we do the condense. So we condense the feature map to retain only the useful part, only the important features. Clear? So this is done by maximum pooling. See, this one is original, this one is pooled. Maximum spaces are removed. Maximum dull spaces are removed. It is more enhanced. Okay. So when applied after ReLU activation, it has effect the intensifying features, and this pooling step increases the proportion of active pixels to 0 pixels. Active pixels are more now. Okay. Now let's add the condense step to the feature extraction we did in lesson 2. This is the hidden code cell. You can just go through it. And now how to apply this one? You can simply write this one. This one max pool 2D, but what is happening in the background? So that is this one. You are calling tf.nn.pool input image pooling type is the max. There are different kinds of pooling type. Here we are using max pooling type. Okay. How max pooling type works? Let me just give you one example. Let's say your pixel looks like this. 5, 6, 1, 2, 8, 9, 5, 4, 7, 3, 2, 1. This is your pixel. Now how max pool works? Max pool takes every block 1, 3, 5, 6. Now it tries to find which one is the maximum. 6 is the maximum, so it will be in the output. Second block, which one is maximum? 4 is maximum, so 4 will be output. Third block, 9 is maximum, so 9 will be here. Fourth block, which one is maximum? 5, so 5 will be here. This will be your output. That is what maximum pool does. So you can see there is no trainable weights. You are not training anything. You don't have any trainable parameters, but you are taking only the largest value in the blocks. That's why this is, you are taking the maximum value. That is, it is called maximum pool. There are other types of pool also, like average pooling. In that case, what you do? You take average of these 4. So 1 plus 3 plus 5 plus 6 divided by 4. What is the value? Will be here. 2 plus 4 plus 1 plus 2 divided by 4 will be here. That is called average pooling. Okay, so there are many types of pooling, but here we are talking about maximum pooling. Now let's understand what is translation invariance. Let me first give you an example. Let's say there is one picture of a Mickey Mouse in the corner. Now in the second image, the same thing but in a different location. Now what do you think? They are same image or different? Both of them are same image. That is the property of translation invariance. So we call the 0 pixels unimportant. We have already said that they are not required. Does this mean they carry no information? They have no values, but what they have a positional information. They carry positional information. The blank space still positions the feature within the image. So when max pool 2D removes some of these pixels, it removes some of the positional information in the feature map. This gives a property called translation invariance. So this means that a coordinate with maximum pooling will tend not to distinguish features by their location in the image. Not to distinguish by the location. Location may be different. So translation is the mathematical word for changing something. See, what happens when we repeatedly apply maximum pooling? These are two blank points. Okay. Now see, after maximum pooling, this has become closer. Second pooling, again the shape is also getting reduced. I have already told you. I have given you an example. See, what is the shape? 4 by 4. Now what is the shape? What is the shape of the output? 2 by 2. So exactly half, because you are taking every block and you are taking only one value. From 4 it is becoming 1. So after every pooling it will become half. 32 into 32. Now it has become 16 into 16. Again half. 8 into 8. This is getting increased because they are getting closer. Now it is 4 into 4. More closer. Now it is 2 into 2. Now very closer. Now what happens? The two dots become indistinguishable. Can you distinguish them? No. In other words, pooling destroyed some of their positional information. Now you agree with this. Since the network can no longer distinguish between them in the feature maps, it can't distinguish them in the original image either. So it has become invariant to the difference in position. Exactly. So pooling only creates translation invariance in a network over small distances, as with two dots in the image. Now features that begin far apart will remain distinct. Let's say one is here and another one is here. They are far apart. Now see what happens. First pooling, shape has become 16 into 16. They have increased. Second pooling, 8 into 8 increased. Third pooling, 4 into 4 increased. But here they have attached, but still you can understand that there is a difference in position. Okay, so some positional information is lost, but not all of it. Okay, so this invariance to small differences in the positions of features is a nice property for an image classifier to have. Okay, just because of the differences in perspective or framing, the same kind of feature might be positioned in various parts of the original image, but we would still like for the classifier to recognize that they are the same. Because the invariance is built into the network, we can get away with much less data for training. We no longer have to teach to ignore the differences. Let me give you one example. Let's say in your image you have 0 0 0 5 0 0 0 0 0 0 again 0. Now you tell me, if I do max pooling, then what will be the output? First block it will be 5, second 0, maximum 0, maximum 0. So this is the output, right? Now let's say I make a small changes. Now I write in this way. Here let's write the 5, 0 0 0 0 0 0 0 0. Same, but the 5 has shifted its position. Okay, it's like a positional shift. Now tell me, what will be the output? 0, 5, 0, 0. So you can understand that 5 is captured in both the places. Though there is a shift, but shifted by 1 pixel, but it is capturing, it is still keeping the strongest value in the output, just a slightly different position. So the feature didn't disappear. That property is very much required. This is what we called translation invariance. Okay. Now this gives convolutional networks a big efficiency advantage over a network with only dense layers. We will understand more in lesson 6 about data augmentation. Now in this lesson we learned about the last step of feature extraction, condensed with maximum pooled. We have completed feature extraction part, which is done by the base part. In lesson 4 we will discuss with convolution and pooling with sliding windows. Okay, now let's do the exercise. So in this exercise, you will conclude the feature extraction begun in exercise 2, explore how invariance is created by maximum pooling, and then look at different kind of pooling, average pooling. Run the cell below to set everything up. Run the cell to get back to where you left off in the previous session. So just give some time, let it run, then we will do that one. Now run this cell to get back to where you left off in the previous lesson. We will use the predefined kernel this time. Okay, see, input, this is the filtered after ReLU. Now we are going to do the condensed part. Okay, so for the last step in the sequence, you have to apply maximum pooling 2 into 2 pooling window. You can copy this to get started. So they have told to copy, so let's copy. Okay, now what you have to do, let me delete this part. You have to give window shape. So window shape will be 2, 2. See, I told you 2 rows, 2 columns. 2 columns, 2 rows. So the shape is 2, 2. You can take different shape also. Here we are taking 2, 2. And what is the pooling type? I told you there are different types of pooling. So here we are taking max pooling. So we will write max. Now let me run this. Okay. Now run the next cell to see what maximum pooling did to the future. See, this is after detect ReLU. You can see that this picture is more enhanced. Okay, the date features are removed. Now we learned about how it works and the property of translation invariance over small distances. In this exercise, you will have a chance to observe this in action. See, the next code cell will randomly apply to a small shift in a circle, then condense the image several times with maximum pooling. Run this cell once and make note of the images that results at the end. See, this is the original one. Shape is 64 into 64. These are the red points, 0 points. Now maximum pooling, these have increased. After maximum pooling 2, the size is 16 into 16. After third pooling, 8 into 8. After fourth pooling, shape 4 into 4. Okay. Now explore invariance. Suppose you have made a small shift in a different direction. What effect would you expect that have on resulting image? Let's see. In this tutorial, we have talked about how maximum pooling creates translation invariance over small distances. We have already understood that if it is near to each other, you cannot differentiate. But if they are far, you can differentiate, right? You have understood that. This means that we should expect small shifts to disappear after repeated maximum pooling. Exactly. But if you run the cell multiple times, you can see resulting image is always the same. And the pooling operation destroys those small translations. Okay. Okay, now next topic is global average pooling. We mentioned in previous exercise that average pooling has largely been superseded by maximum pooling. This is however a kind of average pooling that is still widely used in the head of the content, that is global average pooling. Global average pooling is often used as alternative to some or all of the hidden dense layer in the head of the network. And for that you just have to use global average pool 2D. Now see, just same you have to write layers dot this one. Okay. Now what is this layer doing? Now that we don't have flatten layer. In ANN we have used flatten layer that usually comes after the base to transform 2D feature into 1D. If you remember, let's say you have 5, 15, 30, 75. So what flatten will do? Flatten will make them one dimensional. So it will just simply become like that. This is what is done by flatten layer. But here we don't use this flatten layer. So what we do? We take global average pool 2D layer serving the same function. But instead of unstacking the feature like flatten, it simply replaces the entire feature map with its average value. Though very destructive, it often works quite well. It is destructive because let's say you have 3 channels, red, green, blue. For your image, you should have 3 channels, red, green, blue. Now let's say there is a pixel like this, or 5, 15, 25, 35. So what it does, it just makes an average of them, 10 plus 20 plus 30 plus 40 divided by 4. Okay, so whatever the value is, that is taken. This is what is done by global average pool 2D layer. So let's look on some of the randomly generated feature maps. This will help us to understand how it can flatten the stack of feature maps produced by the base. See, these are the feature maps and this is pooled feature maps. You can see that it is kind of flattened, but we have not used flatten. We have used global average map, which is taking the average value of all the numbers. Okay, this is pooled feature maps. Now, since each of the 5 into 5 feature maps was reduced to a single value, global pooling reduced the number of parameters exactly needed to represent those features by a factor of 25. That's a substantial savings, but you are losing something also. So now we will move on to understanding the pooled features. After we have pooled the features into just a single value, does this head have still enough information to determine a class? This part of the exercise will do that. See, let's pass some images from our car or truck through VGG16 and examine the features after pooling. First, run the cell to define the model and load the dataset. Notice how we have attached a global average pool 2D layer after the pretend VGG16 base, showing found belonging to two classes. See, dataset is loaded. So notice how we have attached a global average pool 2D layer after the pretend. VG16 is a pretend model. Now see how we are applying this layer. So ordinarily it will produce 512 feature maps for each image. And what global average pooling will do? It will reduces each of them into a single value. That is an average pixel. Okay. So let me first run this. This is a car or a truck, and now it will give you 512 average pixels, which is created by the global average pool layer. See, this is the car and this is the pool feature maps. Okay, 512 average values for the pixels. Now you have understood how pooling is working. What do you see? Are the pool features for cars and trucks are different enough to tell them apart? How do you interpret these pool features? How could this check the classification? After you have thought it, run the next cell or see a hint first. See, the VGG16 base produces 512 feature maps. We can think of each feature map as a representing some high level visual feature in the original image. Maybe a wheel, maybe a window. So pooling a map gives us a single number which we could think of as a score of that feature. Large if the feature is present, small if the feature is absent. So cars tend to score high with one of the set of features, trucks score high with another set of features. Now instead of trying to map the raw features to classes, the head only has to work with these scores that the global average pool 2D has produced. So you understood what they have said? Sorry. After you have done the global average pooling, you are getting some score. Let's say this is the score. So if the score is like this, you can tell this is more like a car. If the score is like this, you can tell this is the more of a truck. Okay, that is done by the head part. Head part will check the score and will tell you that what the image is about. Okay. So the global average pooling is taking all the pixels values, making an average, giving you a pooled feature maps, which is giving you a score, and that score is confirming you whether it is a car or a truck. Okay, so we have understood that what global average pooling does. It takes all the pixel values, make an average and give you a pooled feature maps with some score, and after seeing that score the head part will be able to classify the image. Okay. So conclusion, in the lesson we explored the final operation, that is condensing with maximum pooling. Pooling is one of the essential features that helps provide with some of the characteristic advantages. Efficiency with visual data, reduced parameter size, translation invariance, and we have seen that it is used not only in the base during feature extraction but can be used in head part also. Understanding it is essential to have a full understanding of the coordinates. Okay. So in the next lesson we will conclude our discussion with sliding windows, the typical way of describing how the convolution and pooling operations scan over an image. So we will describe our final two parameters in the conv2D and maximum pooled layers, that is strides and padding. Okay. So meet you in our next class. Till then, bye. Happy learning. Hi everyone, welcome back. So we are continuing our computer vision course in Kaggle, and as of now we have completed convolutional classifier, convolution and ReLU, maximum pooling. And today we are going to understand the sliding window. First we will read the tutorial, then we will do the exercise. Okay, but before that let me give you a small recap. As of now we have learned that to understand the type of any image we use CNN or convolutional classifier, and in convolutional classifier you have two parts. One is base, another is head. Base part is used to extract the important features from the image, okay, and head part is used to classify the image. Fine. And in base part we have learned first you have to do filter, which is done using convolution, then detect done by ReLU activation layer, and condense, which enhances the feature, is done by maximum pooling. I hope you remember these things. We have already completed. Now let's start today's class. Okay. So in previous two lessons we have done these things. Now the convolution and pooling operation share a common feature. They are both performed over a sliding window. This also I told you in earlier class, but let me once again repeat it for you. Let's say your image is 1 2 3 0 1 4 5 6 1 2 7 8 9 0 1 1 3 5 7 9 4 2 3 5 1. Let's imagine that this is your image. Image is consist of pixels. Okay, so these are image pixels. Now you have to understand what is the type, right? So for this you take a kernel. Let's say the kernel looks like this: 0 1 0 1 0 1. This is called kernel, or this is called filter. And what is the size of the image? 1 2 3 4 5 1 2 3 4 5. So this is 5 into 5. What is the size of this one? 1 2 3 1 2 3. So this is 3 into 3. Okay. Now what is done? I told you that what we do, we take 1 2 3 4 5 6 7 8 9, and then it is multiplied with the kernel 0 1 0 1 0 1. That means I have taken the first 3 by 3 with the kernel, and then you will get some value. So in the result you will have, let's say, x. Okay. Now second, what is done? Second we take, let's say we take this much 3 by 3. We are just sliding it, multiplied with filter, and you get y. Next, let's say we take this much, z is the output, let's say. Next one, again we are sliding by 1. Okay, you can see that we are taking the next one. So let's say this is A. Now this one, that is B. Now let's say this one. So it is C. So we are sliding one by one. Again we are sliding 1. So again we can take from this. So E, F, G. You can understand. Now next 3, next 3. So it will be completed. Okay. So this is your output result. Okay. So these things we have already covered. Now let's see what they are saying. The convolution and pooling share a common feature. They are both performed over a sliding window. For pooling also, if you remember what we did, let's say 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Here also for max pooling we are taking the max value 6. Next 7. So here also we are sliding the window. Next this one, next this one. Okay, so that's what they have said. For both of them we are using the concept sliding window. And with convolution, this window is given by the dimension of the kernel, the parameter kernel size. This is also, you know, that we used to mention like kernel size equal to 3 into 3 while writing the code. Okay. Now you can give your dimension according to that. It's not that it will always be 3 into 3. You can give anything by providing the kernel size. And with pooling, it is the pooling window given by the pooling size. Whatever you want to take, whether 4 or you want to take like 6. Okay, so that also can be given by pool size. Okay, now these are two additional parameters. Here you can see this one. See, like every time it is sliding by 1. See, okay, so this is called sliding. Now there are two additional parameters affecting both. These are strides and padding. Now before reading this, let me just tell you what is stride and padding in simple terms. See, while we are shifting this, we are shifting by 1. If I tell you that I want to shift, let me just complete this. If I want to shift first this one, then I want to take this one. Again, while coming down, I want to take this one, and let's say one more is there. Okay, and again I want to take this one. Okay, so for first one you will get 1x, second one y, for third one a, for this one b. You are just taking this window and you are multiplying with the kernel or filter. Okay, so this is not like that only one shifting will be there. There may be shifting like this, or let's say you can shift like this. You take this one, then I need one more to make you understand, and next you take this one. This way also you can shift. First one is this one, second one is this one. This way also you can shift. So this is called stride. Okay, now see what is the size here. Here the size is 5 into 5, but after you do the operations you are getting 3 into 3. So you can see the size is reduced, right? Now let's say if I perform this many times, then the size will be reduced to very small. So I don't want that. I want the same size, like 5 into 5 only. So what you can do, you can give a border like this and you keep them as 0. 0 has no value, so it will not change your image. But while performing operations, you are like, let me draw one for you. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. This is 5 by 5. Okay. Now what I am doing? I am doing one more. I am adding one more layer every side. So I am giving like 0 for everyone. So 0, 0, 0, 0, 0, 0. It's like this. Okay. You get my point? Now if I take the window. First I take this one. So you will get, let's say A. Second I get this one. So I get B. Next I get this one. So I will get C. Next I get this one. So I will get D. So you can see already you are getting 4. So your size is increased, right? So it is not reduced in that way. So if you do one more layer, then it will be increased by E also. Okay. So you can change the size of the output by adding some zeros in the original image. Okay, clear? The concept is called padding. So the stride and padding are two concepts which are used. Stride means what is the step you want to take, like how much you want to slide, and padding is adding some zeros so that the size doesn't get reduced. Clear? Now let's read. There are two additional parameters affecting both layers. These are called strides of the window. whether to use padding at the image edges. Now the strides parameter says how far the window should move at each step. I have told you padding parameter describes how we handle the pixels at the edges of the input. See, these are the edges of the input. Okay. Now, how it looks? You have to import kerras, you have to import layers, same convolutional layer. There you are giving 64 filters, your kernel size 3 into 3. This is your kernel. And your strides is 1, strides equal to 1 means you want to shift by 1 position only. Okay. Second, you are giving padding equal to same. Padding is of two types, one is same and another one is valid, that I will tell later. And activation function, you know, that is ReLU. Once it is done, then you are doing max pooling. Okay, this is the part of the base part. Now see, what is stride? The distance of the window moves at each step is called the stride. We have already understood. We need to specify the stride in both dimensions of the image. One for moving left to right, one for moving top to bottom. One is for how you are going this side. So you have to maintain, let's say, by 1 position. Now you have to tell how it will go downside. So that also, let's say, 1 position. So in stride you have to tell two things, by left to right and by top to bottom. Okay, so 2, 2 means movement of 2 pixels each step. See, if you see this one, you can understand. See here, first it is taking from here, second it is taking from here. Okay. Now, what effect does the stride have? Whether the stride is in either direction is greater than 1, the sliding window will skip over some of the pixels in the input. Yes, see, second one is skipped. Okay, so because we want high quality features to use for classification, convolutional layers will most often have strides 1, 1. Because I want to consider everyone. Okay, I don't want to skip anything. I want it to be the best. So most of the times it is taken as 1, 1. But depending on your need, you can change also. Okay, that's a parameter. Increasing the stride means we miss out on potentially valuable information because you are skipping something, so you are missing something. Maximum pooling layers, however, will almost always have strides value greater than 1 because in maximum pooling layer the concept is very different. You are taking the maximum one, so it's better that if you take 2 by 2 or 3 by 3, okay, but not larger than the window itself. Now finally, note that when the value of the strides is the same number in both directions, you only need to set that number. For instance, instead of strides 2, 2, you could use strides equal to 2 for the parameter settings. They just want to say that if you are using same, then you just write 1. Okay, if you are using 2, 2, then just write 2, nothing else. Okay, if you are giving different, then that's a separate thing. Otherwise, you can just write strides equal to 2. That means left to right is also 2, top to bottom is also 2. Okay. Next one is padding. When performing the sliding window computation, there is a question as to what to do at the boundaries of the input. Staying entirely inside the input image means the window will never sit squarely over these boundary pixels like it does for every other pixel in the input. Since we are not treating all the pixels exactly the same, could there be a problem? What the convolution does with these boundary values is determined by padding parameter. In TensorFlow, you have two choices, padding equal to same or padding equal to valid. When we set padding equal to valid, the convolution window will stay entirely inside the input. So the drawback is that output shrinks because here you are not actually doing any padding. Okay, so that means you are actually shrinking the output. Okay, and shrinks for more for larger kernels. This will limit the number of layers in the network can contain. Okay, because if you shrink every time, then your number of layers also have to be reduced. That will be a limit for you, especially when inputs are small in size. They want to say that if your input is already small and every time you are reducing like this, so you have to put a limit on the number of layers. Okay, that's what they have said. So that's a problem. Now, the alternative is use padding equal to same. That means that add some zeros and keep the size same. Like keep it like this only. So then you can put as many layers as you want because every time you are doing padding, you are adding some zeros so that the size doesn't get reduced. Clear? Now, using just enough zeros to make the size same as the input. This can have the effect of diluting the influence of pixels at the borders. The animation below shows a sliding window with the same padding. You can see this is the original one, but they have added some extra every side so that when you get the output, it doesn't get reduced. The size doesn't get reduced. Now VGG model is a very basic model, so it uses same padding for all of the convolutional layers. Most modern coordinates will use some of the combination of two. They are used sometimes valid, sometimes same like this, but VGG uses only same. Okay. Now see an example. To better understand the effect of parameters, it can help to observe a feature extraction on a low resolution image so that we can see the individual samples. Okay, see, this is the kernel. This is the VGG architecture. Here it is the input. First step is filter. Second step detect. It is done by ReLU. And third is condense. This is done by maximum pooling. Okay. And if you use these tools, vision tools, then you can see all the steps. And that works pretty well. The kernel was designed to detect horizontal lines, and we can see that in resulting feature map, the more horizontal parts of the input end up with greatest activation. Now what would happen if we change the strides to the convolution to 3? Okay, see, we have changed the strides. Now input, this is the first step, detect, condense. This seems to reduce the quality of the feature extracted because you have given the strides as 3. That means you are skipping 2 every time. Okay, so you are missing some important features. So our input circle is finely detailed, being only 1 pixel wide. A convolution with strides of 3 is too coarse to produce a good feature map. See, stride 1, the output, stride 3. Okay, so stride 1 is better, they want to say. Yes, because you are not skipping anything, right? Sometimes a model will use a convolution with a larger stride in its initial layer. This will usually be coupled with a larger kernel as well. A ResNet model use 7 into 7 kernels with strides up to. There are different types of models which are already pre-trained on many images. What is our part to do? To import those, to download those and fine tune, right? So they are talking about one more model, that is ResNet model, and the ResNet model uses 7 into 7 kernels for filtering. It uses strides 2 in the first layer. This seems to accelerate the production of large scale features without the sacrifice of too much information. Okay. Now in this lesson we looked at characteristic computation, the sliding window and the parameters affecting in behavior of these layers. This style of windowed computation contributes much of what is characteristic convolutional networks and is essential part of their functioning. Okay, fine. Now let's move on to the exercise. Okay, now in these exercises you will explore the operations of a couple of popular coordinate architecture used for feature extraction. Learn about how coordinates can capture large-scale visual features through stacking layers. And finally see how convolution can be used on one-dimensional data also. In this case a time series. Okay, now first run this cell to set up everything. Then experimenting with feature extraction. This exercise is meant to give you an opportunity to explore the sliding window computations and how their parameters affect. There are not any right or wrong answers, it's just a chance to experiment. Okay, see. This is the circle, this is Kaggle K, this is an image of car, and these are the different types of kernel for edge, for blur, bottoms level. Okay, these are already some kernel in the library. And to choose one to experiment with, just enter its name. So see, you can choose this one, Kaggle K or car. Here they have taken circle 64. If you want, you can simply check with car also. So let me first see this one. See, first filter, detect, condense. Let's see with car. So if I write car, you can check with this also. Let's see. Let's understand what is receptive field. Trace back all the connections from some neuron and eventually you reach the input image. All of the input pixels a neuron is connected to is the neuron's receptive field. Receptive field just tells which parts of the input image a neuron receives information from. Okay, so a neuron is getting information from some part of the image, right? That part is known as receptive field. Now, as you have seen, if your first layer is a convolution with 3 into 3 kernel, Then each neuron in the layer gets input from 3 into 3 patch of pixels except maybe at the border. Okay. Now what happens if you add another convolutional layer with 3 into 3 kernels? See the illustration. See, 3 into 3, then it is getting 5 into 5. How? Now trace back the connections from the neuron at top. You can see that it's connected to a 5 into 5 patch of pixels in the input, the bottom layer. Each neuron in 3 into 3 patch in the middle layer is connected to 3 into 3 input patch, but they overlap in 5 into 5. First, it is connected to 3 into 3, but they also connected to 3 into 3. So ultimately in the second layer they can see 5 into 5 patch of pixels. Okay. So each neuron in 3 into 3 patch in middle layer is connected to 3 into 3 input patch, but they overlap in a 5 into 5 patch. So that neuron at the top has 5 into 5 receptive field. Okay. This neuron is getting information from the image, right? Now it is getting information from which part of the image? That part is known as receptive field. Now if you give the first layer, then it can get information from 3 into 3. But this layer is getting information from 3 into 3 of the next layer. So ultimately it is increasing by 1 each side. So it is getting from 5 into 5. So this one is actually getting from 5 into 5 patch. Okay. Now, growing the receptive field. Now, if you added a third convolutional layer with a 3,3 kernel, then what will be the answer? So, you try to tell. If you add one more layer, then that layer in this one will also get from that layer also, right? So, in that scenario also, it will be increased 1 in each side, right? So, 5 will become 7. Let's check. Stacking the second layer expanded by 1 neuron on each side. So 3 plus 1 plus 5. So if you expand it by 1, then it will become 5 plus 1 plus 1. That will be 7. Let's say what is the answer. See, 7 into 7 receptive field. Okay. So why stack layers like this? 3, right? 3 comma 3 kernels means 3 into 3 9, but you are taking 3 kernels, so 9 into 3 total 27 parameter. But for 7 comma 7 kernel, if you take only one, then also you are getting 7 into 7 49. So though they both create the same receptive field, this stacking layer trick is one of the ways coordinates are able to create large receptive fields without increase the number of parameters too much. Okay, so if you use one 7 comma 7 kernel, you have to work with 49 parameters, right? But if you use 3 comma 3 kernels and you use 3 layers, so what happens? It is giving you 27 parameters. So this is the best way to avoid too many number of parameters, because too many parameters will make the model complex. Now you will see how to do this yourself in the next lesson. Okay. Now, convolutional networks turn out to be useful not only for 2D, but it also works with 1D and video. Video is 3D, time series is 1D. Now, we have seen how it can learn to extract features from 2D images. It turns out that coordinates can also learn to extract features from things like time series and video. So, let's do this. The time series we will use is from Google Trends. Okay. Now it measures the popularity of the search term machine learning from January 25, 15 to January 25, 2020. Let's first run this. It has, see, 2016, 17, 18, 19, 20. Time series on dimensional data. Now what about the kernels? Images are 2D, so our kernels are 2D arrays. But here time series is one dimensional. So what would the kernel be? 1D array. Here are some kernels sometimes used on time series data. See, this is the kernel. -1, 1. It also can be a kernel. This is also can be a kernel. Okay. So convolution on a sequence works just like convolution on an image. The difference is just that a sliding window on a sequence only has one direction to travel, left to right, instead of the two direction on an image. And just like before, the features picked out depend on the pattern or numbers in the kernel. Can you guess what kind of features these kernels extract? Uncomment one of the kernels below and run to see. Kernel equal to dtrend. What happened? Let me run all. Yeah, I missed something. See, this is how it is working. Okay, now the trend means you are actually using this one, -1 1. Now let's use average. So just comment this, stop this. Now see, now it is working like this. Okay, so you can understand the difference in types of features. The D-trend kernel filters for changes in series, while average and Spencer both are smoothers that filter for low frequency. Exactly. You can check with this also. See, they both of them are smoother. Okay. If you are interested in predicting the future popularity of search terms, you might train a ConvNet on time series like this one. It would try to learn what features in those series are most informative for the prediction. Though ConvNets are not often the best choice on their own for this kind of problems, they are often incorporated into other models for these feature extraction capabilities. Okay, so now the lesson ends our discussion of feature extraction and you have gained some intuition. Yes, you have gained, and in our next lesson we are trying to compose conv2d maxpool-d layers to build your own convolutional networks from the scratch. Okay, so let's meet in our next class. Till then, bye, happy learning. Hey everyone, welcome back. So we are continuing our computer vision course and as of now we have completed 4 lessons. Today we are going to do custom coordinates. First let me read this, then we will do the exercise. Okay, see, you have seen the layers of a coordinate uses to extract feature. Now it's time to put them together and build your own convolutional network. Let me just give you a small recap. For a convolutional classifier, you have base and you have head. Base is used to extract the important features from the image. Head is used to classify the image, right? Now in base we do filter using convolution, we do detect using ReLU, and we do condense using maxpool. These things we have already learned and today we are going to build this. Okay, now see. In the last 3 lessons we saw how it does feature extraction, filter, detect, condense. A single round of feature extraction can only extract simple features from the image, simple lines, simple contrast, but that is not enough. So what do? We repeat the same things over and over so that the feature becomes more complex and refined as they travel deeper into the network. So simply they want to say that if you do it once, you can only get the simple features, but you need more complex features. Then only you can identify whether it is a car or a truck, a cat or a dog. So what they do the same thing again and again. Okay. Okay. So they are creating convolutional blocks and it does this by passing them through long chains of convolutional block which performs this extraction. The first block will extract some simple features, comparatively complex, more complex features. Okay, so at this time they will get some complex features which can help you to identify what type of image is this. And in every block the same thing is happening, convolution, ReLU, pooling. Same here, convolution, ReLU, pooling. Same here, convolution, ReLU, pooling. Same thing, but you are repeating multiple times. Okay, so these convolutional blocks role in feature extraction. Okay. Now each block repeats a round of extraction and by composing this block, the coordinate can combine and recombine the features produced, growing them, shaping them and to better fit the problem at hand. Now let's design a coordinate. See, first how to define a convolutional network capable of engineering complex features. In this example, we will create a Keras sequence model and then train it. Okay, so first load the data. Let's define the model. See, in the first block, you are doing convolutional 2D, filters 32, maximum pooling. Same thing, so in the second block, filter is increased to 64. You are doing max pooling. Again, filter is increased, other things are same. Once you have done this, now you are flattening to make it one dimensional, then you are going it through dense layers. Okay, now see, we have defined the model. So our model consists of 3 blocks of convolutional 2D layer and maximum pool 2D layers. Okay, and then you are using dense layer. Now let's see how to write this in Keras. See, first you import Keras, you import layers. Now inside this Keras.sequential, first convolutional block conv 2D max pool 2D. So see here, this one filters 32, activation ReLU, padding same, and then you are using the input shape, that is the image, that is 128 183, and you are passing it to, and you are doing the max pooling. Okay, now in second convolutional block, layers.conv 2D, same, kernel size 3, filter 64, activation ReLU, max pooling. In the third convolutional block, you are doing the same. Once you have done all these things, now you are flattening the layer, you are using dense. Okay, and this is the model summary. Here you can see how many trainable parameters, how many non-trainable parameters. So same thing, see, for first convolutional block, second convolutional block, for third block. Okay, as you wish, you can add more blocks also. This is how you have drawn a simple convolutional network. Okay, so you are building your own. Once it is done, now you have to train the model. So for this, you have to give an optimizer. Here we are using Adam optimizer. Loss is binary cross entropy and matrix is binary accuracy. Okay, now you are storing this in the history. Once it is done, now you can plot, see how it is performing. For that you have to use pandas data frame, and there LOC will help you to do the plotting. Okay, dot plot. So this is the validation loss, see, and this is training loss. You can understand that the model is not performing well because it's a simple architecture, so it will not perform satisfactory. Okay, and this is the accuracy. So this model is much smaller than VG16, so that is why it is unable to fit very well and it is not that good. But you can add more convolutional layers and hoping to create better features. Okay, so now let's do the exercise. In this exercise, you will build a custom component with performance competitive to VGG16. Okay. First run this. Once it is done, this is your component design. So you have to design this with the block architecture like we saw in the tutorial. The model from the example had 3 blocks. It performs on the car or truck problem. Okay, but far from VGG16 could achieve. It might be that our simple network lacks the ability to extract sufficiently complex features. Okay, that is okay. You just have to understand how to start, and later on you can improve the model. And we will keep this block structure. Okay, so let's write this. You have to define the model, and block 1, see, first convolutional 2D max pool 2D. First one is written convolutional 2D max pool 2D. Okay, second block, this one same thing, second block is also written. Now third block they are using 2 convolutional 2D and then max pool 2D. So this one you have to write. Okay, fine. First let me copy this. Now see, this one you have to write convolutional 2D, kernel size 3, filters 128. So filters, this one, filters you have to change 128, kernel size is 3, fine, activation ReLU, padding same. Okay, no problem. And convolutional 2D, kernel size 3, filters 128, same thing. So just do the copy paste. Okay. Next one, max pool 2D. So this is also same. Fine. Now head flatten dense dropout dense. Flatten dense dropout dense. Why dropout is used? Write in the comment section. Now once it is done, let's run this. Done. Compile. To prepare for training, compile the model with an appropriate loss and accuracy metrics for car or dataset. So you have to add loss and metric. See, in the tutorial we used binary cross entropy loss and matrix binary accuracy. So you just have to, you try to write it. I'm just doing the copy paste. Now you can run this. Once it is done, now you can, let's test the performance of this new model. First run this cell to feed the model to the training set. Okay. Now you see 50 epochs, so you have to complete 50 by 50. It was taking too much time, so I have reduced the epochs to 5, and then we have plotted the laws, validity laws, binary accuracy, validity, binary accuracy. It will perform better if you increase the epochs. Okay, so see, this is the binary accuracy, validation, binary accuracy. Now how would you interpret these training curves? Did this model improve upon the model from the tutorial? That it's not improved, but if you increase the epochs here and you give it more time to do the training, then it will improve. Okay. So this exercise showed you how to design your own convolutional network to solve any specification problem. Okay, so in our next class we are going to read about data augmentation. Okay, bye. Happy learning. Hi everyone, welcome back. So let's continue the last chapter of computer vision, that is data augmentation. First we will read the tutorial, then we will do the exercise. So as of now we have learned the fundamentals of convolutional classifier. Let me give you a small recap. Convolutional classifier has two parts. One is base, another one is head. Base part is used to extract the features from the image, and head part is used to classify the image, right? Here we use filter, detect, condense. These things we have already done. For this we use convolutional layer, ReLU, max pooling, right? And head part we do flatten, dense. These things we have already learned, and we have built a simple classifier, but we have seen that that classifier was not performing well, right? So what our concern is now to improve the performance. So how can we do this? One technique is called data augmentation. Okay, so let's read it. See, the best way to improve a performance is to train it on more data. Let's say you have 100 images, but if you have 1000 images, automatically your model will perform better. So you need more data. Now how can we generate data? One method is this data augmentation technique. One easy way of getting more data is to use the data you already have. If we can transform the images in our data set in ways that preserve the class, then we can teach our classifier to ignore those kinds of transformation. For instance, whether a car is facing left or it is facing right in the photo, it doesn't change the fact that it's a car, it's not a truck, right? Let me show you one example. See, this is the original image, but if I flip, if I rotate, if I make it blur, grayscale, contrast, exposure, if I do all these things, will it become a dog? No, this is a cat. So you want your classifier to understand that this is the same image. Okay, so you just ignore these changes. You are telling your model to ignore these kind of changes. Just consider that this is a picture of cat. Okay, so what you are doing, from one image you are creating 6 other images. From one data you are creating 6 more data. Okay, now see, using data augmentation, typically many kinds of transformations are used augmenting a dataset. This might include rotating the image, see like this, adjusting the color, contrast, many other things. Here is the sample of different ways. So data augmentation is usually done online. You don't have to do this, as the images are being fed into the network for training. Recall that training is usually done on mini batches of the data. So this is what a 16 images might look like when augmentation is used. Okay, see, these are the example. Now each time an image is used during training, a new random transformation is applied, and this way the model is always seeing something a little different than what it's seen before. The extra variance in the training data is what helps the model on new data. It's important to remember though that not every transformation will be useful on a given problem. Most importantly, whether transformation you use should not mix up the classes. Let's say you are training on digit recognizer, then rotating images will not work here. If you have 6, let's say you have 6, and if you rotate this it will become 9. That's not correct. So there you cannot apply these rotating techniques. So depending on your data set, you have to understand which one is better for you. And in the end, the best approach for finding this is same with most problems. Let's try it and see. Keras lets you augment your data in two ways. The first way is to include it in the data pipeline. image data generator. The second way is to include by using Keras's pre-processing layers. This is the approach that we will take. The primary advantage for us is that the image transformations will be computed on the GPU instead of CPU. See, in this exercise, we will learn how to improve the classifier from lesson 1 through data augmentation. The next hidden cell sets up the data pipeline. Okay, next you have to define the model. See, import keras, import layers. This is the pre-trained base model. Here you are not starting from the base, but you have a trained model. And now you are using the random flip horizontal. This will flip from left to right, and you are also applying contrast. Okay, so you are changing contrast also. You are using the pre-trained base, and here in the head part you are doing flatten, you are using dense layers. Okay, once it is done, you are training. Optimizer is Adam, loss, binary cross entropy, matrix, binary accuracy. You are storing it in history. Now you are plotting. See, this is the loss, this is the validation loss. This is the accuracy, this is the validation binary accuracy. Now the training and validation curves in the model from tutorial 1 diverged fairly quickly, suggesting that it could benefit from some regularization. The learning curves for this model were able to stay close together. We achieved some modest improvement. Okay, they are saying that we have achieved some modest improvement, but still you can improve more. The more closer they becomes, the more improved your model is. Okay, anyway, let's do the exercise now. In this exercise, you will explore what effect various random transformations have on an image. So, car or track dataset. Okay, fine. So, let me first run this. Once it is done, now we can explore augmentation. See, uncomment a transformation to run the cell what it does. See, this is random flip. Oh, first try with this one, then we will try others also. The factor parameter should be greater than 0 and generally less than 1. Run the cell again if you would like to get some new images. See, I think this is done. Okay, now let's run this one. See, you have done the random flip. Okay, they have just from left to right. Now you can do this one, vertical flip. Okay, see, vertically flipped. Okay, now if you want random rotation, so this is your task to check what is happening with all of them. So it will rotate randomly. See, it has been rotated randomly. Okay. Now in this exercise, we will look at few data sets and think what kind of augmentation might be appropriate. See, they have told you that for if it is a digit, then you cannot do the rotation. 6 will become 9, right? So you have to understand for your dataset which augmentation technique is better. Then you can find the best solution. See, this is Eurosat dataset, consists of satellite images of the Earth classified by geographic feature. Below are the number of images from this dataset. Okay, so what do you think? What kind of transformations might be appropriate for this dataset? This is sea lake, permanent crop, industrial, pasture, residential, forest. Okay, you have to tell which one is best. It seems that flips and rotations would be worth trying first since there are no concept of orientation for pictures. Okay, taken straight overhead. So if you just flip it or you make some rotations, it will not affect. So it will be better. You will get more data, right? Now let's see the solution. It seems to the author that flips and rotations would be same. They have said the same thing. Okay. Now this is TensorFlow flowers dataset. Roses, tulips, roses, sunflower, dandelion. Okay. Now what kind of transformation might be appropriate for this one? You can say if you do rotation, if you do left to right, if you do vertical rotation, if you change in contrast, which one will be the better for you? It seems that you can do horizontal flips, moderate rotations. Since augmentation libraries include transformations of hue like red to blue, since the color of a flower seems distinctive, a change of hue might be less successful. They are saying that roses or tulips, if you change them to something other color, there may be a problem, so don't go for that, but you can do rotation types. Okay. Now you are going to use data augmentation with a custom coordinate similar to the one that you built in exercise 5. So you have to use this pre-processing layer. Random contrast, random flip, random rotation, you can use any of them. Okay. Now see, import keras layer, and here you have to do data augmentation. So what we can do, we can simply copy this. They have told you to copy this only. Okay. So this is the model structure. First, batch normalization, convolutional, max pooling, batch normalization, convolution. You are doing this 3 times, then you are applying head. Okay. Now if you want, you can just run it. Fine. Now you can see the hint and the solution. Now you will train the model, run the next cell to compile with loss, accuracy, find the training dataset. So it will take time because there are 50 epochs. Once it is done, examine the training curves. What there are any sign of overfitting? How does this performance of this model compare to other models you have trained in this course? So once this is done, this will take quite a long time because there are 50 epochs. Once this is done, then you have to you can check the validation accuracy, binary accuracy, validation loss, binary loss. You can see whether it is overfitting, whether the curves, these curves are closer or they are far. If they are far, that means it is either overfitting or underfitting. And if it is closer, then you can understand that the model is performing much better. So you can check the performance. If I reduce the epoch, it will be done quickly, but you will not be able to understand whether the performance is improved or not. So that's why I'm giving you the task that give some time, let it finish, then you check whether it is overfitting or not. So data augmentation is a powerful, commonly used tool to improve model training, not only for CNN but for many other kinds of neural networks. The principle remains the same. You can make up for any inadequacy in your dataset. When you have lower number of dataset, you can simply apply it. Not for only CNN. In other places also, you can use data augmentation. Okay. So that's all for computer vision, and if you are ready, you can apply your knowledge. So congratulations. Bye. Happy learning.